So a little bit of history. This is Dino's first time visiting us here in Utrecht, but he's been in the Netherlands for quite a while already, actually. So after getting his master's degree at Kiev, he moved to the Radboud University in 2011, where he did his PhD in physics. After that, he did a long 4-year postdoc at TU Delft. Got the detour to Regensburg in Germany, and then started his own group at Radboud again in Nijmegen. As assistant professor in 2021. Then he got a nice ERC starting grant in 2022 on, if I recall correctly, antiferromagnetic spin transform the relativistic waves. Right? And I hope you will tell us a little bit on your future plans as well. But first, light-driven ultrafast magnetism. Welcome, Dina.
Right, first of all, I would like to thank Machteld for basically inviting me to come to Utrecht. It's indeed my first time there, and thanks a lot to Michael for organizing, for taking care of all the QuMat. And I also want to thank to many of you whom I already got a chance to talk. Thanks a lot. It was a great pleasure talking to you. So today my talk is entitled Light-driven ultrafast magnetism. So it will be about magnetism primarily, but I will show you how magnetism can be manipulated by using light. What I would like to start is the very, very basic. So I would like to tell you a little bit about magnetism. So my own encounter with magnetism was basically to have a magnet on a fridge. I think it's basically been the case for many of you. But if you like, if you have a look at such a bar, if you look inside, you will see that this bar is made of billions and billions of elementary magnetic moments, which are called spins. So you can see here them pointing to the very same direction, and the fact that they're pointing to the same direction, so they're supporting a parallel spin order, it results into emergence of a net magnetization, which is basically a sum over all of these spins. And so basically magnets which stick to a fridge, they're called ferromagnets. And they're very, very, very popular. I'm pretty sure that you all know about them. And another important thing about them, that basically it's the elementary excitations. The elementary excitations are known as spin waves, and they are nothing else but elementary spin precessions. So basically, such spin precession can be used to carry information also. Because they typically are characterized by dispersion relations. They typically lie in the gigahertz frequency range. Why do we care about ferromagnets? And I think all of you know that basically ferromagnets have been the ground base for many data recording technologies. So even you may think that basically nowadays nearly everyone is using a regular SSD drive, which is essentially non-magnetic. But in fact, magnetic recording using magnetic media is actively present. So in particular, it's basically a part of a Google recovery suite, just used, for instance, to recover your email account if something fails. It has been a big issue in 2011, and when basically magnetic data storage helped to recover all your data. And the main drive why we still use magnetic data recording and storage, because magnetism is characterized by high capacity, low cost, and long durability. So this is a little bit about the past of magnetism, but nowadays it's a very it's a very big development in the field of using basically spin waves as elementary data carriers, which are able to replace electrons. And the main drive of using spin waves instead of electrons is basically the fact that they do not carry Joule heating. So essentially, you can reduce losses significantly. And it has been like a really, really tremendous development within the last 20 years. Basically, the realization of majority gates, which are important for realizing computing with spin waves, and even a magnet transistor has been realized, when actually spin waves can be used to manipulate other spin waves. So basically, I just would like to show you briefly some big, it's basically a print screen of a recent review, where you can see all the basic principal parts of spin wave-based data processing technology. So you can see here sources of basically spin wave generators. You can use basically some wave combiners and ring resonators. All of this has been realized. So basically, they are very, very close to realize on-chip computing with ferromagnetic spin waves. But what's important thing, if you want to realize technology, you need to find a way to manipulate these objects. So for instance, in order to realize magnetic data recording, we typically use magnetic DCB field. So you basically apply field and you can rewrite, you can basically change poles of your magnet, so from pointing up to pointing down, so you can rewrite beats. And if you want to drive spin prestations, basically you can use radio frequency currents, and you can drive resonant spin prestations. So we know how to manipulate ferromagnets very well. And recently it has been a tremendous progress in going beyond of magnetic currents. People use spin polarized currents. So basically it's a current, it's basically electronic current, which has a predominant number of spins pointing either up or down. As such, basically spin current can exert a torque on a magnetization, and it can either drive spin precession or it can lead to complete reversal of magnetization. But what I want to say here, that the tremendous progress of using ferromagnets has been driven fully by the fact that you know how to manipulate them. And these methods have been very, very efficient in manipulating ferromagnets. I mean, what if you're going to go look beyond of ferromagnets? So ferromagnets are not the only magnetic materials, and there's another materials which are known as antiferromagnets, and they're characterized, contrary to ferromagnets, by antiparallel spin order. So here's an example of such type of order. So you can see the neighboring spins are no longer pointing to the same direction. They essentially are antiparallel, and they form a checkerboard pattern. As a consequence of such alternating order is the fact that antiferromagnets essentially are not characterized by net magnetization. Another thing that basically, so this is the thing that they characterized by zero magnetization means they fully coupled to magnetic field. So it's hard to manipulate antiferromagnets by means of magnetic field. Another thing that most of antiferromagnets, in fact, are insulators. So it's not so easy to apply spin currents if you want to basically manipulate them. And what's else very much important, they simply do not stick to a fridge. So why do we really care about them? I mean, I would say this is the main reason for me to think that people think that you don't care about them. So you not always can recognize that the material next to you is antiferromagnet. But in fact, there's a bigger potential of antiferromagnets, despite the fact that they do not stick to fridge, and they're characterized by zero net magnetization. It can be a big advantage. So if you want one day to create memory made of antiferromagnets, and still you can have basically them pointing either up or down, they do not really carry stray fields. So you basically can increase, you can decrease size of magnetic beat. So you can create magnetic memory with higher density. Another thing is a basic abundance of antiferromagnets. I told you, like, it's very hard to recognize materials antiferromagnet. But in fact, if you look up all the materials on Earth, you will see that only 10% are ferromagnets. So most of the materials are antiferromagnets, not visible to us. And being antiferromagnets is typically very often is associated with being strongly correlated material systems. Such system, for instance, might have a metal-insulator transitions. They might have a colossal magnetoresistance, like in manganites. So there are many, many examples of them. Another thing, basically, the fact that they feature significantly higher frequencies on basically their spin waves. They also do host spin waves. And these spin waves are significantly faster. Their frequency in the range of terahertz. So it's basically 3 orders of magnitude faster than those which you encounter in ferromagnets. Basically, if you want to realize one day spin wave-based technology, you can speed it up if you use antiferromagnets. But again, you want to basically benefit from all of these properties. But again, you face issues. They poorly coupled to magnetic field. They are insulators, you cannot drive them by spin currents. And they also require terahertz sources if you want to drive the spin waves, if you want to manipulate the spin waves. And basically, this kind of explains us that novel means of controlling antiferromagnets are necessary. And that's exactly what we do in mining. So I will address the question how to control antiferromagnets without magnetic E fields and no spin currents. And for this, we have to look into basically basics of magnetism. So if you look up on this alignment, you see that these spins are antiparallel. And you may think that basically this alignment is driven by magnetic degrees of freedom. But turns out that the drive behind the magnetic coupling between these two spins are in fact has a Coulomb origin. So this is basically change interaction, which is spin interaction, known as the exchange interaction. It's nothing else but electrostatic or spin-dependent part or residual part of the electrostatic Coulomb interaction. Basically, immediately becomes clear that you don't need to act on spins directly. You basically can act on their orbitals. You can act on the lattice, basically, which hosts these two neighboring ions. In such a way, you can manipulate antiferromagnets. So let me give you an example. For instance, what you can do. So as I say, like it's independent part of the electrostatic Coulomb propulsion, and it depends on so-called change overlap, on how much electronic orbitals do overlap. Essentially, what you can do, imagine that you expand your lattice, or you construct your lattice. So basically, you can control this overlap in such a way you can control strength of the exchange interaction, which is basically the primary reason for antiferromagnetism. You can also try to change the shape of orbitals, for instance, by electrostatic gating. In such a way, you can control change overlap. You can also realize some complex electronic excitations when you realize charge transfer transitions, and you, in fact, can kill antiferromagnetism. So now we can see, I hope, that you can realize non-magnetic means to control antiferromagnets. And you do it by means of light. So we particularly use ultra-short pulses of light, so basically as short as 100 femtoseconds. So at being very short in the time domain, so like this, they are very broad in the frequency domain. So very often they can be as broad as 10 terahertz, which basically means that the problem is driving coherent spin waves in the terahertz range is solved. But there are some other advantages of using light, because light, simply by tuning color of light, you can address different resonances in your material. For instance, you can act on lattice by direct coupling of light to optical photons. So basically, you can address electronic or lattice degrees of freedom, and then to play with lattice contraction and expansion. What you can do, you also can address some orbital excitations, and then you can manipulate basically shape of your orbitals. You can also drive some electronic excitations, for instance, by pumping a bulk band gap. So you can try to manipulate this magnetic state of your media. All right, and indeed, light-driven excitations, this femtosecond pulses of light, has been very, very successful to manipulate antiferromagnets. So essentially, if you look up on the distortion relation of antiferromagnet, which features their frequency and K vector, by means of light, you can address spin waves across entire spin wave band. For instance, you can drive uniform spin precession with a K equals 0, so with a wave number equal to 0. You can realize antiferromagnetic magnet polaritons, so excitations which can propagate together with light, but characterized by still relatively small K vector. But recently, we have shown that you also can generate broadband wave packets of non-uniform spin precessions. So they basically feature very broad bandwidths, so we can drive up to 0.1 terahertz bandwidth spin excitations. And even you can drive so-called two magnum excitation right at the edges of brilliant zone. So basically, you can excite spin waves with light from here up to there, just by using ultrashort pulses of light. So in order to detect, of course, we need to not only to excite spin waves, we need to find a way to detect them. And then we use basically an entire set of tools to do it. So typically, we do so-called time-resolved pump-probe experiment to track dynamics of antiferromagnets. So what we use a pump pulse of a various color, and then we use time-delayed probe pulse, and we can vary a delay between pump and probe pulse. And for probe pulse, basically, we measure time delay, for instance, optical Faraday rotation. We measure magnetic second harmonic generation. Very often, they also measure reverse emission transmission. And on rare occasions, we go for X-rays and electron diffractions. So let me give you an example, actually, how our typical experiment looks like. For instance, like we do magneto-optical Faraday rotation. So here, I plot Faraday rotation as a function of time delay between probe and pump pulses. What you can see here, moment 0, our palm pulse arrives to the sample, it makes excitation, which you can see this excitation moment, and then you get an oscillatory material response, which is in this case is an antiferromagnetic spin precession. All right. So if you look up, if you want to understand basically how it looks,
yeah, you go back to this slide. So is there any kind of nonlinear physics already in this oscillatory signal? Is it just
yet no. This is basically just a damped sine function.
Okay, so it looks very irregular to the eye, but maybe
No, this one is not. This one is moist. So we have to average more.
Also ask a question.
Yeah.
So this Faraday rotation,
Yeah.
is this always like a sharp rotation and an envelope rotation?
What do you mean?
I mean, here you measure a very sharp. It's
I mean here,
yeah.
this is basically like a moment of overlap. So it's basically, I mean, it doesn't really necessarily include Faraday rotation. It can be just like some virtual excitation. So typically, this region of the excitation stays silent to us. So we don't care much about it. We just know our pulse before, and we know material response. This is a very complex part to study. You can study, but it's very complex. So typically, we study what's going there by studying coherent response. So one way to explain you what we do is just to basically have a look on a free energy diagram. So we are dealing with ordered systems where we have basically free energy surface, and we have some kind of generalized coordinate, like basically order parameter. And so what you do, like if you drive spin precessions, you typically drive small oscillations of your system around the equilibrium, right? So basically, you drive back and forth, like your order parameter oscillates, and that's in fact your coherent spin waves. But the advantage of using ultrashort pulses that you can make this dynamics very large amplitude. And how do you drive it? Basically, you can make your system to explore potential energy landscape more and more. And when deviations from the parabolic band might start to play a role, so you might go there and then start more linear part of your coupling. Another basically thing what you can do with light, because your excitations typically in the ratio of few electron volts, you basically can create nonequilibrium, non-thermal state. So instead of exploring this existing potential landscape, your light pulse can induce transient state where your system starts to explore. And this state is not necessarily present in the equilibrium. That basically will be the part which I'm going to tell you about, like how you can create a new states of matter, new transient states of matter, and such a way to optically design new properties of material. And you can do it, like the beauty of this approach, that you can do it very often within the same material host. So basically, the scope of this talk is the following. I will be talking about light-induced dynamics in antiferromagnets induced by so-called phononic excitation. So when we try to perturb your lattice state, and then via perturbation of electrons. And as I promised you, I'll do it within the same material host. So you'll be studying the very same material, just with two different types of excitations. And so materials of choice, it's maybe my favorite material. It's called antiferromagnetic orthoferrite dysprosium iron phosphate. So it's basically dysprosium orthoferrite, and it's basically a complex perovskite, which is characterized by a network of oxygen octahedra and very strong antiferromagnetism. Basically, it can last up to 650 kelvins. And beauty of this material, that it basically hosts two exchange-coupled magnetic ions. There's basically a 3D iron, 3+ ions, and dysprosium 3+ ions. And these ions are essentially very different. So one is 3D and one is like a 4F rare Earth space. They're characterized by very, very different properties. But what's important for us is that their exchange interaction gives a rise to a very peculiar property of dysprosium orthoferrite. So it results in so-called morning phase transition, which takes place around 51 kelvins. So their interaction leads to the fact that there exist two competing states in this material. So basically, there is competing states when spins are fully collinear, so they're antiparallel, but they're still collinear. It's a perfect antiferromagnet. And another state, which is basically when spins acquire some hunting. So it's basically a hunted state, or we call it like weakly ferromagnetic state, because it's characterized by a finite magnetization. And so and basically these two states are in fact competing. So if you look up energy landscape, you can find that essentially the states are separated by a barrier, and depending on temperature, it's either antiferromagnetic state is a ground state, or weakly ferromagnetic state is a ground state. So above 51 Kelvin, weakly ferromagnetic state is dominant. So it's basically a ground state. Another state is a meta state. So let me give you an example of this transition. It's basically a magneto-optical snapshot of this transition. And what you can see, if you are basically above 51 Kelvin, so when your state is weakly ferromagnetic, so you see the energy here is lower, then you get basically very clear, dark and bright striped pattern. Similar to what you see also in ferromagnets, is basically ferromagnetic domains. And they originate because you're characterized by a finite magnetization. And there's this kind of like it's counting either this way or counting opposite way. So magnetization either up or down. But if you start to cool down below 51 K, all of this basic pattern is gone. Simply because there's no magnetization in the media and there's no ferromagnetic domains which you can see. And you can see here around 51 K, energies of the antiferromagnetic phase and weakly ferromagnetic phase are roughly equal. And what you can see here, you can see phase coexistence. It's basically one of the best examples of first order phase transition, where similar to boiling of water when you have a coexistence of vapor and liquid. All right.
Quick question. So
Yeah.
it looks like this is almost like a DC block. So do you really, is it only up or down, or is this just a trick that, I mean, because of the white black, it looks like it's either one or the other, or can you have other orientations of this?
In this case, I think they are only up or down. But in fact, the sample is strained. So because like a way with fluid, it's strained, and the strain defines orientation of domains basically. So you get stripes because of strain. So otherwise, yeah.
I think if you cycle multiple times through the phase transition, the domains appear in the same spot.
More or less, I think they're kind of like
Because
it's a pinning, it's strain, and they're pinned also to defects. But what I want to highlight there, that basically all of this transition is due to interaction between iron and this product. So it's fully governing it, and it's governed by a change overlap between these two. So our idea was basically simple. All right, let's try to deform crystallographic lattice by parting one of the formats in such a way to create distorted lattice with a modified exchange, and such a way to induce this nonequilibrium, non-thermal state, essentially one which we can explore further. So for this, we basically realized photon pumping. So basically, this is our approach. This is approach number one. And we, among all of the modes of dysprosium morphophoride, we pick up so-called BU photon mode. So it corresponds to vibrations of the oxygen octahedra around iron sites. And you can see here optical density. So basically, it's absorption profile of this form. And you can see that basically a form is situated around 80 milli-electron volt. So it's basically in optics, we call it mid-IR frequency range. And for this, you need to have special type of pulses. And basically, we use some nonlinear process to generate such pulses. So you need to play some tricks with your lasers. But after different frequency generation, you can get tunable frequency mid-IR pulses, where you basically can tune the energy from 70, so right here, to 250 milli-electron volts nearly continuously. So basically, it means that if you have such pulses, you have a chance to pump on in resonance with photon and off resonance with photon, and then you can see the difference. And you can see our pulses basically. The electric field strength is on the order of megawatt per centimeter, and you can see the duration of the pulses is on the order of 220 seconds. It's a really, really short excitation, but excitation resonant with the photon. You may ask me, like a 10 megawatt per centimeter, is it a lot or not? I mean, a ionic bond has the strength on the order of 100 megawatt per centimeter. So basically, you can say that we take a 10% of it. And lattice is a very nonlinear object, so it's a big chance that you are able to use some big structural distortion. So this is our experiment. The same way I told you before, we are going to be measuring magneto-optical Faraday rotation. So we will be creating rotation of the light polarization plane, which is proportional to magnetization, and we will be using tunable pump pulses in order to pump off resonantly and on resonantly. So we start with low temperature antiferromagnetic phase. So the spins here are collinear. So we cool down our system below 51 Kelvin. And we first wanted to benchmark response of the system to purely impulsive excitation. So when you pump off resonantly. In the picture which I showed to you already, with parallel rotation function times delay, you get an oscillatory response, right? And if you perform Fourier transform, you see the frequencies on the order of 170 gigahertz. And if you look up literature, you can find it corresponds to a frequency of the spin precession around the microscopic axis. So what you do, you induce like a small amplitude oscillation around the equilibrium. Now we change energy of our pump pulse. So we realize photon pumping. And now we compare directly signals in the time domain. You can see, first of all, amplitude of oscillation is higher when you pump resonantly, but it was significantly more remarkable. The frequency is substantially lower. So it turns out when you excite in resonance with photon, for some reason, a redshift frequency of the spin precession. We were really surprised to see that if you switch to another weakly ferromagnetic phase, you also drive spin precession, but now frequency of the photon-driven spin precession is blue shifted. Essentially, here I have to tell you a little bit about frequencies. So frequency has some magic, particularly magnetism. So all the equations of motion for ferromagnets, also for antiferromagnets, they can be reduced to a second-order linear differential equation. And their frequency is nothing else but a measure. It's basically a second derivative of your potential. So it's similar to a ball, which basically oscillates at the bottom of potential well, like back and forth, back and forth. And the frequency is proportional to curvature of this potential. So it's proportional to the curvature of your potential well. So, and there is also a measure of curvature of your potential well. So here I sum up this frequency versus photon energy. So you can see, first of all, that this frequency shift occurring in the weakly ferromagnetic phase is positive, so it's a blue shift. And it's like resonant with a photon absorption. You can see like they're maximizing there, and they're completely independent if you're off resonant. And they are positive, and they are basically redshifted if you are in the antiferromagnetic phase. But now we know a little bit more about frequency. So basically, what does it tell us? It tells us that the photon pumping not only leads to a blue shift, it basically changes steepness of your local potential. That leads to a curving of your potential. And the opposite happens in the antiferromagnetic phase. So it basically makes your potential more flat. And if your potential is flat, it means that basically there's no restoring force. So your system, nothing brings it back. So you can say essentially that photon pumping destabilizes antiferromagnetic phase, while it stabilizes weakly ferromagnetic phase. All right. Now I'm going to show you a little bit more. So this is about like a local potentials. But if you know curvature of the potential, you are basically able to reconstruct entire potential profile. And here we start. Antiferromagnetic phase here is a ground state. So this is before excitation. And weakly ferromagnetic state is a metastable state. So the system is in this state. And these states are competing. They're separated by a potential barrier. And now we are reconstructing using frequencies, potential after excitation. So here you can see it in orange. So we can see following the excitation, the potential function is changing. And what you can see immediately after the excitation, your antiferromagnetic phase, normal ground state, now it's basically metastable. Its energy higher than the energy of the weakly ferromagnetic phase. You can also see here that I wasn't relying to you. There's this potential around weakly ferromagnetic phase became really steeper. That's basically a sequence of this blue shift, or the reason, sorry, for the blue shift. And another thing what you can see here, the potential barrier between these two phases now is significantly reduced. And one can dream of, and that's something what we also were hoping for, what if we can basically overcome this potential barrier and ballistically steer spins over this barrier? And that's something what we have done. We basically we were thinking about this, as we can do it. And here I plot this time domain traces, basically time delay, further rotation. But here I add up fluence. So basically I plot it for different fluences. So what you can see, if you stay below 10 millijoule per square centimeters, so it's on the order of like a 50, I would say it's on the order of like a 5 megawatts per centimeter. Then basically you drive oscillations, which are essentially redshifted, but not much is occurring. But if you, only their amplitude is growing. But if you go about 10 millijoule per square centimeter, your signal starts to change qualitatively. It basically starts to develop this long-lived offset. And as we are measuring further rotation, which is proportional to net magnetization, these experiments indicate that we are photo-inducing net magnetization in the media. And net magnetization is basically a hallmark of this canted phase. Essentially, we really are able to realize this spin switching. All right.
Do you have any idea on how this happens dynamically as well, this transition?
We do. So what's happening here most likely? So this transition is also accompanied by spin orientation. So it's basically not only that it requires counting, but also the spins basically turn 90 degrees from y crystallographic axis to x crystallographic axis. And what's happening, you drive large amplitude spin precession in a kind of like softened potential, and then basically rotate 90 degrees. That's how we understand it, and modeling shows that it's true. But the main point that basically barrier is lowered there. All right. Yeah.
So I mean, I take these as cartoons. But how much cartoon is it, and how much is it actually meant? Because you say, how do you know that your ground state is actually lifted above your antiferromagnetic state? Is this because you know you can drive the transition, or can you actually see this?
I mean, I think it's. I mean, we cannot really see. I mean, we can only prop local curvature of the potential, so I cannot really tell you about entire potential. I mean, there's a few indications. It's a softening, which tells you about like a destabilization. Another thing that the fact that we can drive information. That's it. The rest is basically theory. And what I totally didn't really tell you, we can discuss it at the very end of talk. It's also how essentially the drive happening, how this lattice perturbation occurs. And this, so because I try to stay completely in the magnetic sector. All right. So again now operate with this mortar, right? So that's basically the very same material cost, but now I'm going to be talking to you about electronic excitations. So about pumping about band gap. And I will show you that you also can create an equilibrium non-thermal state. So I'm going to tell you now about not structural, not magnetic properties of dispersion mortar, but particularly about electronic properties. So dispersion mortar is a classical example of so-called charge transfer insulator. So it means that basically a band gap in this material is given by so-called charge transfer transitions. So these transitions are nothing else but a jump from oxygen side, or like a hopping from oxygen side to an iron side. And this transition has a direct relation to magnetism, because in the superexchange model, this charge transfer of electron is the one which is responsible in this, if you consider like a superexchange interaction, is the one which is responsible for emergence of antiferromagnetism. So basically, if you drive such transitions, there's a quite big chance that you also can perturb magnetic degrees of freedom. And like indeed, it also results into charge transfer band gap about 2.5 electron volts. So what we have shown recently, that if you use such a above band gap excitation, so if you promote this charge transfer transitions, your light is being quickly absorbed in your material. So like it's basically has absorption profile on the order of 59 meters. It basically serves as a confinement of your spin excitations down to a nanoscale. So like this near surface area is excited. It's similar to what you do, like basically if you put basically a pebble into water and you get basically waves because of localization of this excitation. And here you get localization or nanoscale confinement only due to absorption profile of the camera, basically due to penetration depth of your light. And if you make a spin excitation, you basically drive a wave packet of coherent spin waves. And they have shown basically that you can drive spin waves across a band of around 0.1 terahertz. So if you really want to know details, you can go to this and read this paper where we explain basically how it's done. But something what we didn't really understand and what was basically puzzling to us. So basically this data is not really published. So it's our basically current state of the art. That we know that you can drive, like you can reach emission coherent spin waves, which we measure, we are very confident about them. But we do not know basically how we excite spins exactly in this region where this electronic charge transfer excitation takes place. So we simply do not know what's the excitation mechanism of the spins if you found above band gap. And so it's basically a contribution of Victoria, which is also part of QuMat. We did beautiful work on it. So what just before I'm going to go into details of experiment, I want to tell you that there is multiple ways how electronic excitation can influence magnetism. For instance, it's known that in charge transfer insulators, such a charge transfer hopping might lead to ultrafast melting of antiferromagnets order. So imagine that your electron jumps from one side where it's pointing down to the side where another electron is pointing up. So basically, they simply cancel each other. Another thing, it has been shown that charge transfer excitation leads to a deformation of crystal lattices, and that also might affect exchange integral. And also, in some systems, charge transfer pumping might lead to even inducing of ferromagnetic correlations. So it's basically intriguing to understand what's going on there. So our interest is this like a greenish area close to the surface. So we don't care about propagating spin waves. We only care about near surface area. And we basically use magneto-optical Faraday effect in the transmission geometry. So and this Faraday effect, being in the transmission geometry, it basically is sensitive to spatially average dynamics. So it's sensitive to k equals 0. So it doesn't really care about propagating waves. It cares only about this region, which has some kind of uniform profile. And again, we do the same as we do all the time. We contrast below band gap and above band gap excitation. And here we plot Faraday rotation as a function of time delay. So we see just two responses of the system to the very, very same excitation. So you see here the spin dynamics. So it's basically the same spin dynamics which I was talking before. It's very long-lived. It's a lifetime of more than 200 picoseconds. But if you drive dynamics electronically, it's very short-lived. It's basically shorter by 10 times. So it's around 20 picoseconds. So basically, you can sum up this. So here we basically measure dynamics for different photon energies across the absorption edge and I plot relaxation rate. So you can see once you start to pump above band gap, this relaxation rate starts to grow dramatically. So you can do the same experiment, but by trying to increase density of your excitation. So you can see if you start at low fluence excitation, then lifetime is really, really long. But if you start to increase it, not only amplitude starts to grow, but also lifetime starts to shrink down. And basically shrinks indeed like by nearly an order of magnitude. If you want to understand this, what's going on from the physical standpoint, the best way is to look not really on the time domain traces, but on their Fourier spectrum. So here I start basically with dispersion relation. So I plot frequency versus k vector. And there is a spin wave gap. Basically, it's just basically a gap which considers like forbidden spin wave excitation. So in the equilibrium, you can drive spin waves only about 150 gigahertz. And now I plot Fourier transform of this low energy, low pump power excitation. And what you get, basically, you get a symmetric line shape center around F naught. So as expected, because we drive K equals 0. Now we start to increase fluence, 1.2 to 0.8. So we can see immediately that this central frequency starts to shift downwards. So basically, you again develop some sort of like a red shift. And what's even more important, it not only develops red shift, but also bandwidth of your excitation starts to grow dramatically. It acquires some asymmetry, and basically, such a pumping leads to an emergence of the in-gap spin states, and these in-gap spin states typically are forbidden. So how do we understand this? So in 5 minutes, I hope I'll be able to explain to you. So what we believe we do, we believe that by pumping of electrons, we are quenching some of the magnetic interactions. So what if you look up on a Hamiltonian, which describes the ground state of this material, it has 3 main contributions. So it's basically a super exchange interaction, or exchange interaction, which is shown here. It's a Zelensky-Maury interaction, which leads to a canceling of the spins. And there's a magnetic anisotropy, which basically is responsible for the Maury phase transition. And our idea was, all right, imagine that what's happening when our pump pulse arrives, it suddenly leads to a quenching of one of these interaction parameters, like it quenches either J, G, or K, or K2, or K4. And this quenching is principally is basically different along Z direction, and this simply because absorption profile is different. So we start up with quenching of magnetic anisotropy. And what we plot here is basically it's in pseudo color. We plot coherent response of the media. So I plot here frequency versus K vector for different amounts of the quench. What you can see, if you quench magnetic anisotropy, either K2 or K4, K2, K4, you can see that here that you excite spin waves with the positive K numbers. And this is positive because the spin waves propagate away from the surface of your material. You can see here, here, and there. But you can see that not really much is happening there. If you plot the basically Fourier spectra at K equals 0, similar to what we are measuring in the experiment, I mean, you can see that they are nearly centered around the same F naught. The same holds true if you quench K4. So it doesn't really match to our experiment. And situation is very different if you now start to quench exchange and Zelensky-Maury interaction. So you can see in a low fluence regime, you drive spin waves again. You drive spin waves with finite K numbers. But if you start to pump more, if you start to quench more and more, there's basically an emergence of a nearly flat spin wave band, which you can see here is split off the original spin wave gap. So it's better seen here. You can see that you get a central frequency, which is not only red shifted, but also has a lot of asymmetric band, asymmetric weight down to lower frequencies. The same actually holds true if you quench Zelensky-Maury interaction. I have to say that we don't know exactly whether it's Zelensky-Maury or exchange interaction which is responsible for this quench. But one of these is most likely the drive behind the emission of the spin waves and which is happening up on an electronic excitation.
That's a quick question. Maybe I mentioned that these are these LLG type simulations?
Yeah, overall, like it's LG, but like made on a kind of. So we performed them on a. I mean, it's but not they're not really macroscopic basically. So they're kind of like we made a kind of lattice with spins, and then we performed basically on a with a spacing down to like 1 nanometers. Really kind of small spacing on a lattice side.
Yeah.
So it's not really macro kind of LLG equation.
Mm-hmm.
So basically, our experiment shows that electronic pumping leads to emergence of a split off frequency band within the original spin wave gap. And you can see also this band is nearly flat. So maybe wonder basically what can you do with this with such a band? One of the ways is basically to exploit this. I mean, we never did it. Just like I'm going to be like just speculating here. So in disposable multiply, a direct magnet-photon coupling is forbidden, simply because a group velocity of magnets is higher than the group velocity of photons, so they simply do not cross. But if you induce such a nearly flat band, this coupling is now allowed. So basically now you can design interactions between magnets and photons. And I'll make another even more speculations. So there is some similarities with graphene. So in fact, the spin wave distortion in antiferromagnets is linear, at least at large k vectors, similar to graphene. And the same way as by magic angle, you can create flat bands. By electron excitations in antiferromagnets, you can try to create also flat band. All right, so I think I'm already a little bit out of time. So I'd like to acknowledge all these people, particularly Victoria and Jim, who's also my PhD students. I'd like to thank Alexey Kinov, Terrorize, and Boris Ivanov. I would like to thank a lot to Andrea Caviglia and our series, which helped us to understand this electronically induced dynamics in disposable waterfront. So Eugene Bender and his student Rado Andrei, our collaborators from Lancaster University, particularly to Rostislav Mihailovsky, and to Yorit Hortensius and Yaroslav Blanker. And thank you very much for your attention.
Are there other questions?
I have one question. Very nice talk, by the way, like this a lot. But
Thanks.
if you drive the system with, towards a non-equilibrium state, say, can you also, is it also possible to kind of detect the equilibration out of that state to the state to start with, or is that too long?
I mean, most likely, I mean, I think it's possible to do. I mean, in principle, we can extend our basically range of measuring, but typically this is like a thermal excitation because all of your non-thermal excitation eventually turns into kind of like thermodynamics. And we know that equilibration time for disposable waterfront, we did some experiments at Felix recently, so we basically reproduce the data at Felix, and we see that it's basically, if I might be mistaken, but I think it kind of like it's around 1 millisecond, 1 microsecond, which basically heat dissipation. So it exactly matches heat dissipation. So your system is really, really strongly like a non-thermal and out of equilibrium only within some kind of time. And this time is typically when we are measuring so this 100 femtosecond slot, when coherence is still preserved in the medium.
Okay, thanks. Yes.
I have more technical questions. So you show you use a gallium cyanide to generate 2 to 6 terawatt-ish at high field. So can the fundamental titanium sapphire 800 you can do the phase matching already with that, or you have to tune that to other wavelengths? How do you generate? Just very technically. Now you shows like you said you do like from 0.8 to 1.1. Oh, sorry, that's in IR, not.
Maybe show it.
Okay. I get it because I misunderstood. I thought it's use 800 nanometers. So you use IR.
We use IR.
Okay.
So,
Yeah.
So
I see.
Like basically, you need to generate.
You use
some
OPA
pulses.
Yeah.
With a very close energies.
Yeah.
And then you take a basic difference between them.
Yeah. Good.
And then you get tunability by tuning them more and more.
Okay. Do you need also do kind of weird phase matching like this on bits or? This is
you have to do phase matching. Of course, you need to do it like depending on thickness of the gallium cyanide.
Okay.
We still do.
Okay.
That's true.
Yeah, exactly. We'll just keep people in line. Well, in the case, thanks again, Nima.
Thank you.